all of the work that we have done so far is about to pay out and pay out big. This is why. First, we're gonna see that under the assumptions that we have put together, under this additional structure that we have introduced into the maximization problem, the solution of the problem is going to have some very nice properties. First, it's always going to exist. Always. And second, it's going to be unique. And third, it's going to have some very nice economic intuition. So let me spend the next few minutes showing you why. Let me start by reminding you what we have seen so far, which is that many of the economic problems that we will encounter in this course have additional structure that introduces nice properties in the maximization problem. And these properties are, first, that the objective function can be divided into a benefit term and a cost term in an additively separable way, such that the total payoff from taking action X is the benefit minus the cost. Second, we have seen that in many natural circumstances, the level of the action that can be taken has to be non-negative, i.e., X has to be greater or equal than 0. And last but not least, we have seen, and we will continue to see, that in many examples, the benefit and the cost functions satisfy the following properties. Benefits increase with X, in other words, the marginal benefit is positive, but the derivative of the marginal benefit, or the second derivative of the benefit, is less or equal than 0. The cost function increases with X, so the marginal cost is positive. The derivative of the marginal cost, i.e. the second derivative, is non-negative. And furthermore, it is not the case that both are equal to 0. These conditions or properties on the benefit and cost functions of the maximization problem are so important and so useful that we're going to pick a name for them so we don't have to write this mouthful every time we encounter them. And we're going to call them the concavity conditions. We're going to see that the solution in this case takes one of two forms. And which form it takes depends on the following condition, which is whether the marginal benefit at 0 is less than the marginal cost at 0, or whether the marginal benefit at 0 is greater or equal than the marginal cost at 0. Let's look at each of these cases. Consider this one first. This particular case looks like follows. We have that the marginal benefit at 0 is less than the marginal cost, and then we know by the concavity conditions that the marginal benefit function is either going to be flat or decrease, so let's say it looks something like this, and that the marginal cost function is either going to be flat or increase, so it looks something like this. So what does the optimal look in this case? I claim that it has to be the case that X star, the best that you can do, is equal to 0. Now, why is that the case? Well, suppose that you are at X equals 0 and you consider taking the first unit of the action. What is that going to do to your total payoff? The marginal cost of taking this action is all of this height, this. The marginal benefit that it gives you is only this. So therefore, if you remember your calculus, taking that first unit of the action entails a loss in your payoff of approximately this area. And things only get worse with subsequent units of X that you may take, because the distance between the two curves, the marginal cost curve and the marginal benefit curve, is only getting larger. So the additional loss for any additional unit of X that you take gets worse and worse. Now consider the other case in which the marginal benefit at 0 exceeds the marginal cost at 0. That case looks as follows. We have, for example, something like this. As before, the marginal benefit function is going to be either flat or decreasing, say something like this. The marginal cost function is either going to be flat or increasing, say something like this. In this particular case, I claim that the solution is given by X star given by the equation, by the solution to the equation, marginal benefit equals to marginal cost. Let's see why. Well, clearly at zero, being at zero cannot be an optimal or a maximum, because if we take the first unit, we get an increase in our payoff equals to this height, and only an increase in the cost equal to the marginal cost at zero of that unit equal to this much. So that will increase our total payoff by all of this much. We can keep playing this trick until the point in which the marginal benefit curve and the marginal cost are equal. At that point, the total increase in payoff obtained by taking the extra unit cancel each other, and we don't get anything. Any subsequent increases after that will entail a loss of total payoff because the marginal cost curve is above the marginal benefit curve. Here is another way to think about the intuition from the solutions that we just characterized. Consider what is the marginal value of taking an additional unit of x, let's say, of delta x, which we can denote by the marginal value of the objective function, which given the additive property is going to be equal to the marginal benefit minus the marginal cost. Now, we know from the concavity conditions that the marginal benefit function is either going to be flat or decreasing, that the marginal cost function is either going to be flat or increasing, and that implies that the marginal value of taking an additional unit of x on the total payoff, which is the sum of these two, is going to have to be decreasing by the concavity conditions. Okay? So the basic idea here is that the value of taking an additional unit of x is never increasing, and in fact is getting worse and worse. Now, what does this mean? This then means that there is a very easy way of thinking about the solution, which is you start at zero. If the marginal value of taking a unit of x is positive, let's say if the marginal t looks like this, you take it. And you keep going until the marginal value of that thing gets zero. And then you stop, because any subsequent unit is going to entail a loss in payoff. Consider the following two remarks that I hope will strengthen your understanding and intuition for the results. The first one addresses the question of whether, under the conditions that we have provided, is it always the case that there is a maximum? And the answer is no. In many cases there will be, and it will have the properties that we have just seen, but the maximum may not exist. And here is the pathological example that some of you may have been wondering about. So suppose that for example, your marginal benefit function is flat, which is something that is allowed by the concavity conditions, and that your marginal cost function is increasing, but for example, it increases asymptotically like this, and it never crosses the marginal benefit curve. Now, it's easy to check, and you should verify this if it's not obvious to you, that these curves as drawn satisfy the concavity conditions. And yet, there is no maximum in this problem. Why? Because since the marginal benefit of doing another unit always exceeds the marginal cost, the individual is better off by keeping producing more and more excess. So the only solution is to go to the infinity, i.e. there is no maximum. Strictly speaking, the case that we have presented in the previous example cannot be ruled out, and therefore under the properties, and specifically under the concavity assumptions, a maximum may not exist. However, I want you to know that I consider this somewhat of a technicality, because most of the examples that we will encounter in this course and most of the problems that we will solve do not have that very extreme property or extreme features. And the reason is because most of the examples that we will encounter satisfy what are called crossing conditions. These crossing conditions state that as x goes to infinity, as the quantity taken becomes very large, either the marginal benefit goes to zero or the marginal cost goes to infinity on both. Let's see why that helps us root that very extreme example in which no maximum exists? Well, if as x goes to infinity, the marginal benefit goes to 0, or the marginal cost goes to infinity, it's very easy to see that these two curves have to cross at some point x star, which guarantees the existence of a solution. Now consider another very basic question that many of you may have been wondering about. Why is it that there is at most one maximum? i.e., why can there not be multiple points that maximize the function, the objective function? The intuition is actually pretty simple and can be depicted graphically easily. Suppose that you have a point like x star that is a maximum, say an interior maximum, then we know that the marginal benefit and the marginal cost curves must have crossed at that point. Now, however, because of the concavity conditions, we know that when we move to the right of this point, given that marginal cost was equal to marginal benefit here, to the right of this point, marginal cost must exceed marginal benefit. That means that these curves can never bend back and cross again. And that means that x star must be the unique optimum necessarily. The results that we have developed in this section are so extremely useful for your study of economics that I want to highlight them as a key result of the course. And this is what I would like you to memorize and of course understand. That is, if you have a maximization problem that maximizes over a non-negative action, an objective function that is the difference between a benefit function and a cost function, and that this benefit and cost function satisfies the concavity conditions and the crossing conditions that we have studied, then it has to be the case that there exists a global maximum, that it is unique, and that it's given by the following properties. It's equal to 0 if the marginal benefit at 0 is less than the marginal cost at 0. Otherwise, it's given by the solution of marginal benefit equals marginal cost. I am aware that for many of you, the material of the last 20 minutes has not been trivial and perhaps has been too mathematical and too abstract. But please believe me that if you understand the key result that I just gave you, it's going to give you a lot of power to solve problems throughout the course and to understand the key intuitions and the key reasons for some very, very basic and important results in economic theory. So I urge you to go back and look at these results if you have not fully understood it, to really grasp. It's really an investment not only in the class but in your understanding of economics. The good news is that now we can put this into use and you're going to see how quickly we can solve very interesting problems just by applying what we have learned so far. So let's do some examples.